So thanks a lot for introduction. As I will have next 40 minutes of your lifetime, that makes me always a keynote speaker at Tango community collaboration meetings. That makes me really proud and happy about that. So I will give two talks, as Jean-Michel announced. The first one is a bunch of different benchmarks I've done over the last year, and it will take roughly half an hour. And the next one is a story how we hunted down this random timeout bug at CORBA. So let's get started. As the first one talk, I split it into different episodes. As I was rewatching the Star Wars movies back then, I prepared the presentation. I split it into episodes and tried to make it in the style of Star Wars. So episode one.
Igor, it's hard to understand you. It's hard to understand you. Can you somehow speak louder or go to the microphone or something? It's just low voice.
Okay. Is it better now?
Well, for me, it's okay. Torsten,
yeah,
perhaps
better.
it's yeah.
Yeah, maybe it's a problem of bandwidth, but well, I have quite a 1 gigabit network here, so should be fine from my side. So anyway, the episode 1, Revenge of Java, and I also prepared this to be aligned with the Star Wars epic text. I won't read it right now. You can read it afterwards in the recording. But the whole fuss about is that the poster I came across last year, or should I say long ago, in a galaxy far away, when we were allowed to travel in New York at Ecolabs conference. There was a poster about Tango benchmarking, and specifically this part, which tests write attribute performance on a different against different servers. So Tango server written in C++, Tango server written in Java, and Tango server written in Python. So here we see the C++. It's almost 1 million. The time scale is not usual. Usually it's 1 second, but here we have 15 seconds. So all my benchmarks further also takes usually 15 seconds. So this one is C++, this one is Python, and this one is Java. And you see it's like very low. That looks very suspicious to me, because if you Google just Java performance versus anything, you usually end up on very hot discussions. And I just took one from Stack Overflow. And again, I won't read in detail through it, but basically modern Java can easily outbeat even C++ performance, because if you just follow the guideline on how to program in Java, the JVM will do a lot of work for you to optimize the code. It even compiles parts of the code in a native code. So actually some methods are executed in native speed. And there is also different levels of optimizations and so on and so forth. And so simply can't be just very low. So I've extracted this Java benchmark server from the repository, which was like sys-tango-benchmark something on GitHub, and ran all my tests against it. And this is my test case. So this is a Java client. Basically what it does, there is a loop which creates a number of threads, so clients. Usually it's 64, again, due to the poster information. And what it does, it creates a Tango attribute proxy, then writes some value infinitively for 15 seconds. And then I just see the number on the client side, and then compare it with the number which gives me the server side. The same client for C++. So again, it's in a loop creates a number of threads, which are basically clients, and we have a device attribute proxy, write attribute, increase counter, and so on and so forth. So basically, these are two almost identical if we do not care too much about the syntaxes in different languages. And these are my first results. I performed my tests on 2 physical nodes with a real network between them. So average ping looks like this. So quite fast network, but still these are really separated physical nodes. And here are some numbers. So if we talk about C++ clients, again 64, and run it against the Java server, so that one which is used in the benchmark on a cold start, which means that JVM usually takes some time to, so to say, warm up when it analyzes the code flow and what can be optimized, what can be de-optimized. So usually after several minutes, Java shows better performance. But I ran all my tests against the cold start, so these are like lower bound, lower limit of the possible performance. And I tried with different transaction mode, which is available in Tango-Controls, so like without transaction mode, attribute, and so on and so forth. And I also played a little bit with the thread pool. Yeah, thread pool comes from JCorb, so the CORBA implementation of Java. And as you can see, the 5 is the default value. The performance is really low, so it's what we see on the poster. But if we increase the thread pool to 200, then it's already comparable with Python. And the problem is JCorb implementation of CORBA. So the thread pool there, it's really poorly implemented, and as you can see, if we use this 5 threads, it like creates for every client, almost for every client, a new thread, then tries to do something. And as you can see, even the simple test for 64 clients and 15 seconds produced almost 100K threads on a operating system, which is obviously hits performance very hard. So to fix that, and if you use Java servers, make sure that you tune JCorb thread pool and define the minimum and the maximum values to be equal, otherwise it doesn't work, and as much as expected clients to be. But in the following tests, I usually use 200, even if the clients are significantly more. So let's get back to numbers. Now, as we explain this performance whole due to the thread pools, so we can then compare really C++ with Java server. So I ran my client test against C++ server, so basically Tango test and double scalar writable attribute, and C++ gives me this number, so it's comparable, right? Again, we have a problem with Java client because it's bounded to 200K requests per 15 seconds. And this is obviously a bottleneck in the Tango ORP implementation. On another hand, I tried to run this test on a single node, even though they were the Tango server and the client were deployed in Docker, or client was run natively and on the server was in Docker. But anyway, this was a single physical node. And in this case, we actually see this performance hit by C++. So it's almost 1 million requests, as we saw in the poster. Again, Java is only 340, 400K something. So some conclusions to this point. So I guess that the picture that was on a poster was actually, as far as I remember, the tests were run on AWS, and probably AWS deployed everything on a single physical node, maybe in Docker, but looks like it was a single physical node. Then we can explain this performance hit in C++. So if you use Java server and you have to tune JCorb set pool. And when the clients and the servers are separated by a real network, performance is more or less the same for every implementation. So Java, Python, C++, they all show the same performance on the server side. And Java client is limited by 200K. So if we go to the real picture, and if you want to estimate performance of your system, of your deployment, and you use a real network to communicate, then probably the picture will look like this. So this is the upper limit, and you will have a linear performance gain due to the concurrency multi-threading on the server side. So this is the end of episode 1. If you want to try, on all the source code is deployed at the GitHub repository, so you are free to take it and try yourself. So next episode, CORBA Phantom Menace. Okay, so I did a small homework implementing different transport listeners for Tango, specifically ZFQ and HTTP transport. With very simple Tango message processor and integrated into the Tango Java API. It's in our fork, so it's the D fork of JTango. Pull request 38, so you can grab and try it. Basically, it provides new methods to admin device. So there is attribute supported transports. So now there are 2, ZMQ and HTTP, and a couple of, well, actually there is a single method, upgrade protocol. So you can switch from CORBA to ZMQ or HTTP. In a client, it looks like this. Again, this is a Java client, almost identical to what I used to test for tests in the previous episode. But now when we create a divide proxy, we can actually upgrade protocol to HTTP or ZMQ. The rest is the same. We just write attribute and increment and get the counter, which means that now we can speak directly to a Tango server through HTTP. And here in this video, you see how I write a new value to an attribute using post request with a content type application JSON, where I say action read or write, which device, target is attribute, data type, and the value. So see, it was like 64, and now it's the write returns nothing. And if we read again, it's 128. And this also means that we now can use enterprise standard tools over HTTP directly to Tango services. So here I use AutoCannon, which is very well known within the front-end community, which tests the performance, so basically latency, how many requests the front-end can process. Here is from 1,000 clients. 1,000 clients for 5 seconds. So we can now run this tool, and it really communicates with the Tango server directly. So again, I run my tests on 2 physical nodes because it doesn't make sense, I think, to run it on a single node. I'm pretty sure 99% and 99.999 installations will use real network between servers and clients. So and here are the numbers. So first of all, C++ client, which is basically CORBA. You know the numbers for thread pool 5, 200. With thread pool 1, it gives 200 something K requests. So these are just to compare it something. And Java clients, well, these are actually uses this upgrade protocol feature. And here are the numbers for write and read attributes. So if we write to a Java server with call start, I mean no warm up or JVM, with a very naive and simple implementation of simplest ZMQ pattern request reply. So it gives us 230K something performance. Again, this is all on a 15-second scale. Interesting enough that if we try to, let's say, implement some thread pool on a server side using a request routers pattern for ZMQ with the thread pool 200, the performance is even worse than if we just make a single request reply. And in case of HTTP, I used the HTTP 2.0. With the thread pool 200, it's something about like 130K. These are for writing, and for reading, ZMQ even better than C++, a little bit. So it gives us almost 300K, while HTTP gives 170. So, and here are some things to think about if we want to go this way. So obviously we will need some fire and forget strategies for ZMQ. So push pull, pops up, and so on and so forth. For asynchronous messages, so I've tested only request reply, so the synchronous communication, but I believe that any synchronous communication is a corner case of asynchronous communication, when you just fire some request and then wait for a reply based on the IDs and so on and so forth. We should consider marshaller and marshaller performance. I just grab code from Tango server side to wrap everything in CORBA objects and then pass it to the server side from the message that I receive from the client. And there is also a lot of things that affects the server side performance, like transaction mode, black box, device lookup, and so on and so forth. Client side thread pools, and finally, nice feature would be implement everything on top of non-blocking IO. And there are even more things to think about, and it's very convenient that you will have this 1-hour session of strategic thinking in the end of this day. So maybe you would like to bring these points on the table. So the question is, how many efforts will it take to outbeat CORBA performance? Is it really required? I mean, there may be some cases where you just need a slow control and you emit one request in, I don't know, a minute just to move some water or something like that. And then embedded HTTP will allow seamless integration with modern enterprise systems, because 99% of them are built on top of HTTP nowadays. We can make an embedded REST API. So imagine every Tango server is basically an HTTP endpoint, and which provides all its attributes, commands, and so on and so forth. And again, this is like a revolution versus evolution strategy, because if we look at this transport listeners, it's very easy to embed them into admin device. So they all share method bind, and somewhere in admin device, when the Tango server startups, it creates this, in this case, it's HTTP server, and then it just binds to some, to each network interface and listens on it for an incoming HTTP request. And then we have an HTTP handler which takes the message using marshaller. This is incoming message I showed you in the video previously. Then we process it, given a back message, and then send it to the as a response. And if we talk about the Tango message processor, it's basically a single line which can be replaced with some kind of Tango internal event bus, submit a message, and then we can incrementally add the services to this bus, like login service, black box service, I don't know, whatever else service, authentication service, and so on and so forth. So you see that then we can incrementally add new functionality, written new code, completely independent from the existing code base. In the meantime, we will have the old system running, and compare the performance, test against it, and then eventually we can migrate everything and say, okay, now we do not need the old code base, just remove it, and we will have all the services around the system. So if we look at the processor itself, it's very easy. I only implemented read and write for attributes. So basically it receives this Tango message, and then it says device read attributes. This is an internal API available in Java. I don't know if it's available in C++. And then we get in the CORBA any object, extracted, wrap into the message, and send back. More or less the same for writing. We have a device, we write attributes, and then just send an OK message. So next episode, a new RxJTango API, where Rx is reactive extension. So there is this reactive manifesto published on 2014, and this basically says how you should architect your system. They call such system reactive systems, and this is nowadays it's basically a standard of any big enterprise application. I don't go deep into details. The important thing is that there are 4 important points that must be met to claim that the system is reactive. It must be responsive, resilient, elastic, and message-driven. So there is tons of information out there in the internet. You can easily find anything you want. And the most important thing about that is that reactive extension itself. So nowadays it exists for almost any platform, almost any language. There's a couple of nice books. As they all share the same philosophy and almost same implementation details. If you read one, you can easily write code in any other language because they're all the same. Basic idea is that they introduce so-called operators. So here in the top, you have a message flow from different sources, typically. And then you can perform some operation like zip or merge, as it was in the previous video. And this affects how you get your messages. And there are tons of such operators. You can perform almost any operation. So for instance, here we say that we want to get only distinct numbers. So 1, 1 is skipped, you get only 1, then 2 and 3, and so on. So what I did, I implemented a couple of classes that actually implements reactive specification and bind it to Tango. Again, the code is extremely easy. We have a reactive extension to Tango. And this is a glue code to the reactive API. Inside we have a future, and the future might be like a reading attribute, executing command, reading pipe, whatever. So here are some examples. This is a reactive code. So here we have Tango event attribute change publisher, which connects to Tango event system and listens for the changes in the state attribute. And using reactive extension, I can say that I want to take only first 100 events. They are emitted every 10 milliseconds, so I take only first 100. And in the second example, I say that I want to receive only an event after on each second. So I receive an event, then I skip how many, 100, and then get another one, and so on and so forth. So this is useful for, let's say, GUI clients, which might be in the mobile network, and they do not want to be so much processing the data. They say, I just want a value of 1 second and so on. And here's another example. Using reactive API, I can implement very easy this well-known feature of Tango. When you subscribe to an event, underneath it performs a synchronous request to the Tango server, so you get immediately a value from the Tango event system, which you cannot recognize whether it's a real event or it's just a value. here you just say, okay, I subscribe to state, and here we will replay the last event in the system. So when client comes in, it immediately gets the last event from the system. So this is how we can emulate this behavior of synchronous request while Tango subscribes to events. And since this thing of reactive streams is very useful, we decided to start a new project where we'll have this reactive stream in the very center. I mean, it might be not, it's very simplistic representation of the whole idea. Sorry. And we want to be able to speak to different actors, where each actor doesn't care about counterparty. So for instance, if we have a GUI, for instance, Waltz UI, we can take values from Tango, from Apex, from Dukes, and in GUI, we do not care from which source it comes. We do not need to know the API of any upstream system. We only deal with this reactive extension in our language. So for instance, this can be a Python script. For instance, imagine here it's written Python, and then you use this RxPython, connect to the reactive stream and get all the data flow, and you can very fine control what you want to do with it and how you will process it and so on and so forth. So this lies in this repository. So if you're interested, you can go there and explore. For now, we have a experimental implementation based on HTTP and server sent events, so SSE, and I run some benchmarking against it. So it's a single physical node for this magic client. It's basically a client to this reactive stream and the server, which is this green box in the center. So it's deployed on Tomcat instance. Then we have a real network to the Tango benchmark server, and the performances looks like this, 60K something. And this we can easily explain, because if you remember, the raw HTTP endpoint to a Tango server gives us 120 something. And here we basically perform 2 HTTP requests. So, and we also now have an implementation, which is in production now in Korean synchrotron, where the small installation that operates a spectrometer and it's built on the system, but not on HTTP and SSE. Uses different protocol called air sockets, which is reactive sockets. And for bigger installation, of course, we plan to use Kafka for the streaming. So conclusion, there is a lot of space of improvements, which is great. Much worse when there is no space for improvements. And then we come to the last episode of this talk. And I call it the Clone Wars. So if we think about any possible implementation of connecting, let's say, HTTP and Tango API, usually it looks like this. So we have an HTTP endpoint, then we have some REST middleware, and the Tango API in the very bottom. So why clones? Here on the left-hand side, we have REST server, which is, I forgot to add links to the repository. So this is basically a REST server, which is part of the standard Tango source distribution. So we have an HTTP endpoint, then we have JAX Rx Java REST middleware and JTango API, the HTTP fork underneath. And then I tried to play a little bit with its clone. Again, we have an HTTP endpoint, but then we use NodeJS Express as a REST middleware and the CPP Tango to talk to Tango. So here are some numbers. So first, it's Java, and we write from 1K clients, and the performance is like 75K request, and average latency is 200 milliseconds. So you can see everything here in the table. So this here is here we see a detailed table of latency. So you see that 99% of the clients have somewhat 300 milliseconds delay, and still we have 80K requests processed. But if we start to read and enable all the optimizations that are allowed implemented in the REST server and reading from 1K clients, so 1,000 clients, yeah, you see the latency is like 200 milliseconds, but like 50% of the clients just wait only for 40 milliseconds. And we can process 320K requests. And that means that for monitoring or for slow control, this installation is just perfect. I mean, it's more than we can expect. And the clone of it lies here in this repository. Basically the same thing implemented with Node.js and C++. So writing from 64 clients, so we can still process about 80K requests, but average latency is like 11 milliseconds. If we write from 1K clients, so now we same numbers with Java, it's again 80K requests, but average latency almost 200. And if we go to 10,000 clients, we still process somewhat 80K requests, a little bit less, because we have a lot of timeouts, like 2K timeouts, and average latency is then always almost 1.5 seconds. So this is the end. What I would like to give you as a main takeaway from this talk: always carefully consider your goals and your path to achieve that goal, so to say. So if you want to blow a planet, then obviously you will need this thing. Otherwise, you might need this thing. And thank you. If there are any questions, yeah, I can also.
Thank you, Igor. Yeah. It's very, very interesting. You have only 10 minutes for the next one, so I propose to not skip the questions for this time.
Okay.